Victor Veliadis, you are the Executive Director and Chief Technology Officer of Power America. One of the missions of Power America is to bring down costs for manufacturing wide-bandgap semiconductor devices. What is your approach to achieve this target?
So the role of Power America is to accelerate commercialization of silicon carbide and GaN electronics. I think people today are aware of the benefits that this technology bring, not least of which are the environmental benefits. So from the onset, the program was set, like you said, to increase manufacturing, get to volume manufacturing, and drop the cost. So what I did is I identified the different areas of wide-bandgap device efforts, starting from the material itself, try to improve the material, lower the cost. Then I looked at the devices. What is it that we need to do with respect to fabrication? How can we fabricate more efficiently? And how can we exploit the silicon infrastructure that is massive and due to its economies of scale can help reduce costs? Then the next step is the module. You can have a great device, but without a module, you have nothing. So I looked at the modules, and then at that point, I started looking at the reliability. You want reliable devices and you want devices that are rugged, and then system applications. And that's the last step, which is the most important step, because if you do system applications and show benefit, then companies, government will further invest in these technologies, and the goal is to get to economies of scale. If you increase the volumes and you get to economies of scale, that will drop the cost. Now, there are certain aspects of silicon carbide, for example, where you have labor-intensive processes, so economies of scale are not going to bottom out. But for those items that I mentioned, once you invest with them and solve some of the problems, then collectively, synergistically, you can bring the cost down.
So the bottom line of your presentation today was that on system level, wide-bandgap devices are competitive to silicon today. Why do you draw this conclusion?
Right, so it's counterintuitive in a way, because when you spend 3 times more, roughly, to buy the device, the assumption is that when you make the system out of silicon carbide or GaN, it will be more expensive. However, at the system level, because silicon carbide and GaN can operate efficiently at very high frequencies, you're able to reduce the size of the passive components, the magnetics, so the overall system cost actually drops, is actually in certain cases lower than what it would be in silicon because of the lower volume, the lower weight, and the thermal management that can be a little more reduced in the case of wide-bandgap semiconductors. So there are examples out there of people who have done this study and they've looked at the cost of the materials using silicon carbide and silicon, and of course they'll pay more for the silicon carbide device, but they will make up that difference in device cost at the system level because of that reduction in passive components, and that's of course the fact that you're capable to operate at high frequencies efficiently. Now that's the upfront cost that doesn't take into consideration the savings you're going to have from having something that's more efficient over the lifetime of the product. But people usually don't want to hear that for 20 years you're going to be saving energy, so you will make up the money that you pay more upfront. They really want a cost-competitive upfront price. And I think in certain applications like PV, we're already there. I think in applications like the adapters for laptops and cell phones, you have that combination of higher performance, faster charging that comes with a cost that's similar. And that's a huge selling point. And it's the case for silicon carbide as well. And it's only going to get better down the road. Onboard chargers, traction inverters, as we increase the volume, they will also fall into that category where cost parity with silicon is going to happen.
Today, at 650 volts, all the 3 major power semiconductor technologies compete each other: silicon, silicon carbide, and gallium nitride. Do you think all these 3 will serve this market, or will at least silicon carbide leave that market and go only for the higher voltages?
So if you look at silicon carbide, it started at 1200 volts. It didn't start at 600 volts, and there was a good reason for that. At 1200 volts, it has more advantage over silicon, Now, the big market at 650 is due to the fact that you have the automotive, which is massive, and for that reason, silicon carbide started going down to the 600 volt level. I think that its material has its place. For example, if you're in an application where efficiency is not of great importance to you, you can have a little lower efficiency, or in an application where you don't care about the mass and volume, right? Their silicon will be very, very competitive. It's rugged, it's very reliable, people know how to design it, so it's a good solution. If you look at applications like aerospace or electric vehicles, right, where you have more confined space and where being able to shrink the size really helps you, people would be willing to even pay a little more to get those advantages through silicon carbide and GaN. So I think that all three materials are very competitive. There's a lot of room for growth for silicon carbide and GaN in terms of reducing the defects and increasing performance. I don't want to say that silicon has reached its limits, because every time you say that, there's some new improvement that's happening. So certainly silicon is making progress, but I think there's a lot more room for improvement in silicon carbide and GaN that are in an earlier stage of development. So I think all three materials will be competitive in that voltage range. Now, as cars are moving rapidly to an 800 volt system, the competition will shift to 1200 volts. What are your solutions for 1200 volts? And I think there, wide-bandgap materials are even more effective, more competitive with respect to silicon, with respect to 600. So with the AV market being such a huge market, I see the shift to 800 volt battery will have silicon carbide and GaN being maybe taking a bigger market share than what they would have at the 600 volt range.
So which future trends do you see with silicon carbide coming the next few years?
So silicon carbide has demonstrated high voltage devices. 10 kV devices have been demonstrated in JFETs, MOSFETs as early as 2006. IGBTs at 15 kV have been demonstrated in silicon carbide, and there's even a paper from Wolfspeed where an IGBT is doing 27.5 kV. Now, there are a lot of applications that call for those high level of voltages, and of course the biggest one, and it's an umbrella of applications, are grid modernization, where you bring in all the DERs, where you bring in all the renewable sources. That's a huge application for silicon carbide, and that's a place where these devices can play a major role. And also, again, the AV market that seems to be driving both silicon carbide and GaN. If you look at fast charging stations, where you can go and have like 10 cars lined up, in parallel and having their battery charged, that would require higher voltage to be more effective. So I think certainly silicon carbide has a very competitive road for EV, competing with silicon, trying to get design wins in this massive market. But I think the next step of development would be those high voltage devices.
You think also of solid state transformers, do you?
Absolutely. That's part of the grid infrastructure that can greatly benefit from high voltage silicon carbide device. So I think the 10 kV will be the first device to be commercialized, and then people are going to start looking at the IGBT. Now, the IGBT in a way is a different animal. So getting the 15 kV IGBT, you have to basically design the lifetimes and so on and so forth. So it's there's a lot more science and work to be done, but I certainly think that we'll be moving in that direction. So getting to 15 kV with IGBTs and going even higher, those voltages really harness the capability of silicon carbide. So we'll see them in the future in grid applications.
And the future trend you see with gallium nitride, we saw 2 presentations about bidirectional GaN. Do you see also this coming?
Yeah, so what I see for GaN, for one thing, first of all, the really large application that has led to economies of scale, really dropping the cost of GaN, is the commercial adapters, consumer electronics, huge application, volume applications. GaN also has the advantage that there are non-power devices, there are GaN RF devices that are made in very large volumes for 5G and RF type of applications, and those kind of tie together. That's part of the overall volume for GaN. So all this work can lead to improvements. So I think GaN will continue to have that stronghold in consumer electronics and dominate there. I think GaN does have a future, more in the more near future, for the onboard charger, that has lower power, so you don't need to parallel many devices to get to the current levels that you need. And certainly there's work that's being done in the traction inverter, where it's competing with silicon carbide and silicon. And certainly in the lateral device version, I'm not talking about the vertical version that might be materialized in a few years, but certainly the lateral devices that will play in that field for sure. And also, like you mentioned, this bidirectional capability is due to the fact that you have a lateral device. That's exactly why you're able to do this bidirectional device, and it's the exact reason where you cannot do one with silicon carbide, because silicon carbide is a vertical device. So I think the bidirectional device will open up a lot of applications, and of course the big advantage that it has is that really you're getting bidirectional capability from a device that has the same area, more or less, of a unidirectional device. If you look at silicon carbide, because it's vertical and you cannot do that, to get the same capability you need to put two devices back to back, and that doubles the resistance, creates connection problems, and so on and so forth. So I think there's a lot of room for applications and growth in this GaN bidirectional lateral device.
So Victor, thank you very much for this insight.
It's been a pleasure to see you here in Germany, and happy to talk to you anytime.